children, welcome to Form 5 Lower Chemistry first term. Today we are going to learn energetics. Here is the content for you. We are going to learn the exothermic and endothermic reactions, energy level diagrams, and enthalpy change or heat energy changes, which is in short form we say delta H, and specific heat capacities and bond energies. You can refer the specification from 3.1 to 3.8 and the textbook page number 207 to 223. Here are the learning objectives. Know that chemical reactions in which heat energy is given out is exothermic and in which heat energy is taken in is endothermic. And describe simple calorimetry experiments for reactions such as combustion, displacement, dissolving and neutralization. And calculate the heat energy change from a measured temperature change using the expression Q equals mc delta T, and calculate the molar enthalpy change delta H from the heat energy change Q. Children, let's learn about systems and surroundings. What is a system? A system is the part of the occurrence we want to study. For example, when we are carrying out a reaction, whatever is happening at the reaction mixture, in the reaction mixture, that's what we call a system. And what is surroundings? Surroundings is anything or everything beyond the system, right? Let's look at this picture, then you will understand better. Okay? Here in this picture, you can see a crucible is being heated. That means the salt is present in the crucible, right? So here, the contents of the crucible are the system, and the Bunsen burner and all the other things are the surroundings. Okay? Have you understood now? Only the reaction mixture in the crucible is the system. So other than that, everything else is surroundings, right? So here what is happening? Heat energy is supplied to the system. That means energy is transferred from surroundings to the system. Okay, children? Have you understood? Okay, here is the heat and temperature. Children, we always use these terms heat and temperature, but we hardly able to know the difference between these two terms, right? Okay, what do you mean by heat? Heat is the energy that is transferred from one object to the other due to a difference in temperature. Now, what is the temperature? Yes, the temperature is a measure of the average kinetic energy of a body, right? Now you know how you measure the temperature using a thermometer, right? That is the bodily energy. That means the average kinetic energy of a body, right? So hereafter, don't mix up the heat with temperature. Okay. Now, heat is always transferred from objects at a higher temperature to those at a lower temperature. Okay, children, have you understood now? Right. Children, let's classify the reactions in terms of measuring heat. So here you can see two thermometers. So one is named as exothermic, in which the temperature rises, and the other one, that's blue color, endothermic, in which temperature falls, right? So let's see what is this exothermic and endothermic, right? Here you can see the energy is being transferred from the reaction mixture to the surroundings. That means that's the beaker of water. Understood? That means the energy is being transferred from system to the surroundings, right? So such reactions are called exothermic reactions, in which heat is given off or heat is released from the system, right, okay, to the surroundings. So that's why temperature of water rises. That's why here in thermometer you can see greater temperature reading, right? And on the other side you can see the heat energy is being transferred from surroundings to the system, that is to the reaction mixture. So heat energy is being absorbed or taken in by the system or reaction mixture. That's why the temperature falls in the blue thermometer, right? So such reactions are called endothermic, right, in which heat is taken in and temperature of water drops. Understood, children? Yes. Right. Here we are going to look at the exothermic reactions a bit more. Already you know the definition of exothermic reaction or process. A change in which the heat is released. Okay? In a chemical reaction, if the heat is released, such reactions are called exothermic reactions and the process is called exothermic process. Here is an example. You can say something burning, right? Any object or even the fossil fuels burning. When something burns, what is evolved? What is released? Heat is released. Okay? Heat is released. So, burning fossil fuels is an exothermic reaction. Okay, children? Okay. Once again, burning fossil fuels is an exothermic reaction because they release heat. So these are the examples of reactions, some more, right? So one is hydrogen burns in oxygen producing water and lots of heat. So here is an equation where you have 2H2 plus O2 gives 2H2O. So here generally in this reaction heat energy is released. And the second reaction is the acids with metals, okay? The reaction of acids with metals. This reaction is also an example of exothermic reaction because lot of heat energy is released. So how do you know that the heat is released? Because you can see the beaker where you are carrying out the reaction, right? So that beaker gets warm. Okay, children? Okay. And then the third example is neutralization reactions in which you are neutralizing an acid with alkali. So definitely when you use a thermometer in a neutralized mixture, the temperature obviously rises, okay, which means heat is released. And the other example is displacement reactions. So there is one reaction that's called thermite reaction in which iron oxide is being decomposed. That means the aluminium displaces the iron from iron oxide and only iron forms. So this reaction releases a lot of heat. So this is also an example of exothermic reaction. Okay, children? Right. Now, endothermic reactions. So what did you learn about endothermic previously? Yes, the reaction in which the heat is absorbed or taken in. Right. Okay, a change that requires or absorbs the heat. Right. So here are the examples. So one best example for endothermic process is what? Yes, photosynthesis. Right. So photosynthesis is an endothermic reaction in which energy is taken in by the plants. What is the energy here that plants take? Yes, light energy, right? From the sun or heat, we can say that, right? So this is the light energy. Sunlight is absorbed. Okay, children? So here are some more examples of endothermic reactions, right? So one is thermal decomposition of metal carbonates, right? Where without heat, these metal carbonates do not decompose. So you have to provide heat. That means the reaction mixture absorbs heat. Then only it can decompose, right? So one is copper to carbonate decomposing to copper oxide and carbon dioxide. So you can see green color copper carbonate on heat turns to black copper oxide, right? And the second one, zinc carbonate, right, decomposing to zinc oxide and carbon dioxide. In this reaction also it absorbs lot of heat, right? And the other one is calcium carbonate, the best example of a decomposition of metal carbonate. So calcium carbonate on heating decomposes to calcium oxide and carbon dioxide. Okay, children? Right. Children, let's look at this endothermic and exothermic reactions in terms of bond breaking and bond making. Okay. In any reaction, in reactant side, the bonds are broken. Okay. So, for the bonds to break, energy must be supplied. Okay, children? Once again, for the bonds to break, energy must be supplied. Look at this. So, here is a compound and it is bonded. So, how do you break this bond? So, to break this bond, energy must be supplied. So, here what happens? Endothermic process. So, it happens in the reactant side. And on the other hand, when the chemical bonds are made, the energy is released. This happens on product side. All the products, in the products, the new bonds are made. So, for that process, energy is released, right? So, look here, there are two elements and the new bonds are made so that the energy is released, which means on the product side always exothermic process happens. Okay. So, a reaction is exothermic if more energy is released than is supplied. That means product side more energy is released, right? And a reaction is endothermic if more energy is supplied, that means absorbed or taken in, than is released. Okay, children? Children, let's classify the reactions in terms of measuring heat. So, here you can see two thermometers. So, one is named as exothermic, in which the temperature rises, and the other one, that's blue color, endothermic, in which temperature falls, right? So, let's see what is this exothermic and endothermic, right? Here you can see the energy is being transferred from the reaction mixture to the surroundings. That means that's the beaker of water. Understood? That means the energy is being transferred from system to the surroundings, right? So, such reactions are called exothermic reactions, in which heat is given off or heat is released from the system, right? Okay, to the surroundings. So, that's why temperature of water rises. That's why here in thermometer you can see greater temperature reading, right? And on the other side you can see the heat energy is being transferred from surroundings to the system, that is to the reaction mixture. So, heat energy is being absorbed or taken in by the system or reaction mixture. That's why the temperature falls in the blue thermometer, right? So, such reactions are called endothermic, right? In which heat is taken in. Now, enthalpy. So, it is symbolized as H. What is enthalpy? The heat supplied or removed is equal to the change in a thermodynamic property called enthalpy. Once again, so heat supplied or removed is equal to the change. Okay, right. So, it is a Greek word, enthalpy means, which is heat inside. What's the meaning of enthalpy? Heat inside. So, it is symbolized as delta H is the symbol for the change in energy. Once again, delta H is the symbol for the change in energy. Right. A change in enthalpy means what? What do you mean by change in enthalpy? A change in the heat absorbed or released. Okay, children? Enthalpy, hereafter enthalpy means what do you say? A change or chemical reaction in which heat is absorbed or released. Okay? Children, let's look at this exothermic and endothermic reactions and how we are going to display in energy level diagrams. Okay, the first reaction is exothermic reaction. So how we are going to display this energy level diagram? Look at this. Yeah, exothermic reaction pathway. That means as the reaction is progressing, you can see the products are placed below the reactants, which means the products have less energy content. Understood? So you can see that's the reason why delta H is negative, because the products are placed below the reactants and they have less energy, right? So in an exothermic reaction, the products have less energy than the reactants. Okay, and you can see on y-axis we have mentioned the enthalpy, and on x-axis course of reaction. That means the reaction is in progress. Understood, children? This is how you have to display. So in exothermic reactions, always the reactants are above than products, and products are below the reactants. Okay, children? So reaction examples you have already seen, but we will have another look at them. So exothermic reactions, now already you have seen, reactants produce products and energy is as heat, it is delta H is negative, right? So here is another example what we have seen before, right? Something is burning and lot of smoke is evolved, that means lot of heat energy is released. Another example you can see, children, have you seen this hand warmers in the cold countries? They use these hand warmers. That means the heat energy is released from these hand warmers to our body or to our hands, right? So energy is released from these hand warmers to keep ourselves warm or to keep the hands warm. So are these examples enough? Right. Now let's look at endothermic energy level diagram. So in exothermic you have already seen that products are below reactants, but here what happens? In an endothermic reaction, the products have more energy than the reactants. That means products are above the reactants because they have more energy, right? So let's look at the diagram. Yes, this is the endothermic energy level diagram. So as I have already mentioned, the products are above the reactants and delta H is positive because the arrow is denoted upwards. Okay, so delta H is positive, right? So here you can see the while the reaction is progressing, right? So heat energy is absorbed. That's the reason why products are above the reactants. Okay, children? Right. So let's look at some examples. Okay, here is a opposite of hot packs, right? So this is cold compress when people are bruised or having a lot of heat in their bodies, and sometimes when they get the joint pains and all, they use these cold compresses, right? So that their bodies can become cool, and these cold packs absorb the heat from certain areas of body or from your bodies, right? Understood? So absorbing energy means it is endothermic, right? So this is another example, that is already you have seen this crucible being heated. So what is happening here? The salt in the crucible will get decomposed by absorbing the heat energy from the Bunsen burner. Okay, so here the heat is absorbed or taken in means endothermic process. Okay, children? Right. Now, how do we relate change in temperature to the energy transfer? Let's look at this. So we are using calorimetry. It's a process, right, in which we measure the amount of heat absorbed or given out in chemical reactions. Okay, so for this we need a medium, right? So look at this calorimetry. So this is a simple like apparatus in which we use a copper lined beaker, right? So which we cover it with the lid and we use the thermometer which is placed on the spirit burner, right? So water gets slowly heated up and we can measure the temperature and we can measure the temperature rise, right? So initial to final temperature. Okay children, this is the calorimeter, simple calorimeter. And using this calorimeter we can measure the heat capacity, that is heat required to raise temperature of an object by 1 degree Celsius. That is what you call heat capacity. Okay. Children, we have seen about the specific heat in the previous slide, right? Now we are going to learn about specific heat capacity. It is the amount of heat needed to raise the temperature of 1 gram of substance by 1 degree Celsius. That means if you want to raise the temperature of any 1 gram of substance by 1 degree Celsius, how much amount of heat is needed? That is what gives you the specific heat capacity. So in most cases it is the water we are going to measure the specific heat and sometimes other substances as well, right? So by using this formula we can measure the specific heat capacity, that is Q equals mc delta T, in which Q is amount of energy in joules and m is the mass in grams, C is the specific heat capacity, that is joules per grams per degree Celsius, and delta T is change in temperature. So you can measure the change in temperature by subtracting the initial temperature from final temperature. Okay children, once again how do you measure? By using the formula Q equals mc delta T. So here is an example question to measure the specific heat capacity. So how many joules of energy are absorbed by a pot of water with a mass of 350 grams in order to raise the temperature from 25 to 30 degrees Celsius? And the specific heat of water is given, that is 4.18 joules per grams and degree Celsius. Right. So here is the formula. Q is mc delta T. And you already know what is the mass of water, children? Yes, 350 grams, and you already know the specific heat of water, that is 4.18 joules per gram degree Celsius. And what is the temperature difference or change in temperature? Right, final temperature is 30 and initial temperature is 25. So when you see the difference and then substitute all these values in the formula, you will get 7315.0 joules. Okay, why did the units become only joules when there are other things like grams and degrees Celsius? Because you know that in mass grams and in temperature degrees Celsius both gets cancelled with the units mentioned in specific heat. So finally you end up with only joules, right? Okay children? Yes. I have given the exercise questions for you to practice. So think and take your time to practice them, right? And substitute the values, right, in a proper way. Okay. Now, once again, I am going to remind you what is an enthalpy. Enthalpy is the heat absorbed or released in a particular reaction, right? It's a change in heat energy, right? So how are we going to calculate this enthalpy of any unknown reaction or any known reaction? So you can calculate by using this formula, that is delta H equals heat of the reactants or heat energy of all the reactants minus heat energy of all the products, right? In other words, we can say, as I said, when the bonds are broken, right? So heat is absorbed. When the bonds are formed, heat is released. And another thing I have to tell you children, in reactants, always in reactants bonds are broken, and in products always the bonds are formed. Okay, right. So you can see if you want to, if the answer is delta H is negative, then you can straight away say that reaction is exothermic, right? And if the delta H is positive, then you can say that reaction is endothermic. Understood? If the delta H is negative, exothermic, delta H is positive, then it is endothermic. Okay, children? Right. Now, how do we relate change in temperature to the energy transfer? Let's look at this. So, we are using calorimetry. It's a process, right, in which we measure the amount of heat absorbed or given out in chemical reactions. Okay. So, for this we need a medium, right? So, look at this calorimetry. So, this is a simple like apparatus in which we use a copper lined beaker, right? So, which we cover it with the lid and we use the thermometer which is placed on the spirit burner, right? So, water gets slowly heated up and we can measure the temperature and we can measure the temperature rise, right? So, initial to final temperature. Okay, children, this is the calorimeter, simple calorimeter. And using this calorimeter, we can measure the heat capacity, that is heat required to raise temperature of an. Now, I am going to give you a bit of a definition about bond enthalpies more. That means, as I have already said, energy is needed or required to break the bonds in reactants. That means reactants always undergo endothermic process, right? And energy is released when chemical bonds form. That happens in the product side. That means always products undergo exothermic process, right? So, by comparing the energies for breaking bonds in the reactants and forming bonds in the products, one can approximate the enthalpy change for a reaction. Okay, children, once again, by comparing the energies for breaking bonds in the reactants and forming bonds in the products. So, you can calculate the enthalpy change for a reaction. So, let's calculate the enthalpy change for the reactions taking some examples. So, here is the enthalpy table. So, for certain bonds we have, you can see here. So, bond enthalpy values give the average energy to break a chemical bond. You all have already learnt, right? So, here are given OH bond, single bond OO and carbon and oxygen bond, and oxygen double bond and carbon oxygen double bond. So, you have the enthalpies, right? Values are given. And all these values are given in kilojoules per mole, right? That is the unit. Okay, children? Right. So, here we can calculate. So, there are certain rules you have to follow to calculate bond enthalpy, right? So, one is that first of all you have to draw the structural formulas to know how many bonds are broken, how many bonds are made, and list the number and types of each kind of bond broken and formed. And so, always you know that bond breaking is endothermic. So, you have to add all the reactant energies, right? And bond formation is exothermic. So, you take all the overall or total heat energy of the products and you have to subtract it from the reactants. Then, when you calculate, you get the enthalpy, right? Okay. So, here is an example to calculate the bond enthalpies, right? So, this is a combustion of methane and the equation is given as methane plus 2O2 gives carbon dioxide and water, right? 2 water molecules. And their respective bond enthalpies are given for CH bond, oxygen-oxygen double bond, carbon-oxygen double bond and hydrogen to oxygen single bond enthalpies are given, right? What is the first rule to calculate the enthalpy? Right. First you have to display each compound in the reaction. So, compare the reaction and this displayed formulae of each compound. So you have two oxygen molecules. So this is how you can display the two oxygen molecules. And then one carbon dioxide. So you have two carbon to oxygen double bonds. And you have two water molecules. So from each water molecule you have two hydrogen to oxygen bonds. So in two water molecules you have altogether 4 hydrogen to oxygen bonds, right? So when you substitute these values in the total energy of reactants in which the bonds are broken, right? So 4 carbon to hydrogen bonds and 2 oxygen double bonds. So substitute their respective bond enthalpies and you will get 2648 kilojoules. And in the products, for the new bonds to form, you have 2 carbon to oxygen bonds and 4 hydrogen to oxygen bonds. So substitute their respective values and you get 3342 kilojoules. And when you substitute the total energy of reactants and the total energy of products in the formula, H reactants minus H products, that is enthalpy, right? So you get 694, that is minus. So when the delta H is negative, what is it? The reaction is exothermic. Understood? If the enthalpy is negative, means it's exothermic, children. Okay, children, this is how you have to calculate the enthalpy from the bond enthalpies. Okay? And here is the summary. So whatever we have learned so far, exothermic reaction that gives out energy and forming new bonds gives out energy, right? It happens in reactants. And endothermic reaction, that is takes in energy. Breaking bond takes in or requires energy. And specific heat capacity is the amount of heat needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. So its formula is Q equals mc delta T. And bond enthalpy is the energy required to break a covalent bond in the gaseous phase. So we calculate using the formula delta H equals H reactants minus H products. So here are the practice questions, children, in exercise 2. So focus well and specially doing the displayed formulas and calculating using calculator, right? So that's the end of the presentation of the lesson, children. Hope you have learned all the definitions in the endothermic and exothermic reactions and the examples and the calculations of specific heat capacity and the bond enthalpies. So thank you for listening and have a good day. Stay safe.